Yes, my friend, what was your question?
I just want to say hi.
Oh, okay. Hi. So I was just trying to put on the recording device. Okay. Thank you all for coming. Uh, so one last thing over here. Thank you. Yes. All right. So I think to kick this off, some of your friend came to me this office hour, today's office hour. Then I think there was something interesting that you have done. That'd be cool to share it with all the students. So it was about using the MLE to find, using the MLE method. Let's find the MLE for Poisson distribution. So Poisson distribution with rate that is lambda. And from there, where we can check whether such distribution is biased or unbiased. I think that would be a good preparation for. And then there are some of the assignments that I want to go over with you. So this will help in the, in clearing up what the methodology look like. So remember, Poisson distribution, you can stop me at any time, okay? So for the Poisson distribution, which is a discrete random variable, the PMF is the function f of x that is actually there's lambda to the power x raised to the power x, okay, divided by factorial x with exponential minus lambda. So lambda is a rate of the distribution. So we want to find the MLE for this Poisson distribution, and then prove that this MLE is unbiased. Okay, so let's do that. Okay, so so we said, yeah, hi everyone, thank you. So we said that we need a sample x1, x2, xn. So taken by the random variable x, which is of a Poisson type, like we said in this case. Okay, so next we need to find the likelihood function. Likelihood function. Capital theta. So the capital L theta, so it's the product, say k, that goes from 1 up to n, like this, of the PMF f at xi. So that is the product, k that will go from 1 to n of, well, actually, lambda x indexed by k divided by x factorial exponential of minus lambda. Okay, that's this product. So I can use some algebra to do that. So this will be exponential, this term L theta, it's exponential of minus lambda raised to power n, because you'll be multiplying the exponential of minus lambda n time. And then, that multiply lambda raised to the power x1 plus x2 plus etc. plus xn. Then you divide all these terms with x1 factorial x2 factorial, x3 factorial, etc., xn factorial, like this. Okay, so once we have that then we can manipulate a little bit this expression. So it will be, well, actually exponential of minus n lambda with lambda raised to the power, this summation, you can write it as a function of, and the mean, it's nx bar, you can check that. So that one multiplied by 1 divided by the product by I that goes from 1 to n xi factorial is that product. Okay, then to continue the process, we need to take the log of the expression. So that will be log, the natural log of all the expression exponential of minus n lambda with lambda raised to the power nx bar 1 divided by the product xi factorial, I that goes from 1 to n. So we close all this. Then you apply the logarithm term for Twitter. So the product become a sum. It's natural log of exponential of minus n lambda, like this, and plus the natural log of, well, actually lambda raised to the power nx bar plus, well, the natural log of 1 divided by the product xi factorial, I that goes from 1 up to n, like this. So the left term that I have over here will disappear, and this term become, well, log exponential is negative x, so that will be n lambda plus, I can drop the nx bar log of lambda plus log 1 divided by pi, I that goes from 1 to n xi factorial, like this. So that's the log of capital L of theta. Okay. So once you have that done, it becomes a function of lowercase l of theta that equal again minus n lambda. Repetition is not a bad thing. X bar log of lambda plus the log of 1 divided by the product. I that goes from 1 to n xi factorial, like this. Then with theta that belong, well, the theta is just a parameter, okay? So anyway, so then to find the critical points, you will take the derivative respect to theta of L of theta, and with respect to lambda, the variable, the theta here is lambda. It's lambda. So it's with respect to lambda. Okay. So when you do this derivative, you find the negative n over here plus nx bar and 1 divided by lambda, okay, plus nothing. So then we set this equals 0 to find the critical points. So this will give us n, that is nx bar divided by lambda. And so the lambda that we get will be nx bar divided by n, and gives us x bar. So the hat lambda is x bar. I've saw something in the chat. Let me take a look and then what is in the chat. So how do we know how many parameters there should be? No, because in the Poisson distribution, you only have one single parameter, right? It's lambda. So the parameter basically is related to, well, it depends on the distribution function. So you know that for an exponential distribution function, it is one single parameter. For a beta distribution, it's 2 parameters. For gamma, it's 2 parameters. For the normal distribution, it's also 2 parameters. So if you want, that knowledge of theta is connected to the knowledge that you have under the probability density function or the PMF. Did I answer your question? Did I answer your question? Okay, thank you for the question. So you have for the Poisson, I have the MLE, which is X bar. Okay, so it's a good example to prove how to do this. Then next, we want to check whether it's biased or unbiased. It's this MLE unbiased or biased. So usually what we do to find that out, it's we transform the lambda at which is X bar. So it's a function of x1, the deterministic x1, x2, x3, etc., xn, like that. So there is another question. What is the significance of theta in L theta since theta isn't a parameter? No, yeah, that's what I did. So the parameter lambda here is my theta. Okay, so I can just write that the theta is the lambda. Does that answer the question? Yes, okay. Thank you very much. Keep asking question if there are some of the stuff that are missing. So what we do is we'll replace the deterministic variable with random variable. So like this, x1, x2, up to xn. Then, we see what the expected value of lambda hat is, x2 up to xn. So So this is just the expected value of the sum of capital Xi divided by n, because it is, it's just the mean, which is the sum of the Xi divided by n. So I will take 1 divided by n out because of the linearity, and I'll also take the sum out, I that goes from 1 to n of exponential of Xi. But the Xi, they are Poisson random variable of parameter lambda. So each of the Xi that goes from 1 to n. It's a Poisson distribution with parameter lambda. So the expected value of xi is the rate. It always has been the rate. So this become E of the sum xi divided by n will just become 1 over n. So which multiply the sum I that goes from 1 to n of n, which multiply lambda. Okay, so put it over here like this. It's not n, but it's just lambda over here. So if you sum lambda in time, you will get n lambda divided by n. So this is lambda. That's exactly what we anticipate if the random variable is unbiased. So if you want the conclusion of this is the expected value of like this, x1 to 3 up to n, it's lambda. So hence, the MLE, this implies that the MLE lambda hat is unbiased. So I wanted to do that as a practice purpose. Then we can come back to the other type of assignment. Any question, guys? All right. Yes, go ahead, Jeff.
I have a question. My
Speak
question.
louder. Speak louder. Maybe let me raise my volume. Then there are a few questions in the chat that I'll take. Yes, my friend Jeff, go ahead.
Okay, so for differentiations, if we get for actually it's for the MLE function, the L function. After differentiating it, if we end up with two values, do we have to see the second derivative and see if it's bigger or smaller than zero?
Yes, so you mean if the theta is a pair, right?
Yeah.
So if it's a pair, you don't do it like that. So you
Okay.
will, for the a pair case, then we change the page case. So meaning the theta is theta 1 and theta 2.
Oh, okay.
Then someone is knocking. Give me a second. Oh, he just, I think he went for a break.
Okay, thank you.
Yeah, sure. Sorry about that. So what you do is you find the L as a function of theta 1 and then theta 2. So the next thing that you do if you want to find,
Do we take partial
yes,
derivatives of each? Okay.
absolutely. It's like you are finding the critical point for two variable function. Okay. So there is another question here in the chat. Are we required to prove all these just now the result? What do you mean? I don't think I get that question very clearly. Are we required? There is a question in the chat that is more private. I'm reading it for everyone. Are we required to prove all this just now? The result is okay. But I really don't see what you mean. But what you mean is, do we have to do each of the steps to prove the unbiased case? I'll say yes. But if okay, so if some of within such step, what I did here is I use the fact that if you take a Poisson distribution, its expected value is lambda, the rate. So that one you don't have to repeat the process. Okay. Was that the question? No. Oh, so there is another question in the chat. Okay, there is another question. Will we be given all distribution function or should we? Look, I think I addressed that question already. I said not to memorize anything. I don't have myself all of those things on top of my head. But so if I ask to memorize this and don't memorize the others, but it look like I'm giving away what the test contain. I don't want to do that. I can guarantee you that whatever is in the test is at your level of knowledge. But learn some of those distribution. Don't memorize them, just learn them, write them down a certain number of times. You will see that you will become used to them. There is no point of memorizing anything for these tests. Okay, guys? Thank you very much. So now let's take some of those assignments and see. Okay, do some of them. Sorry, I need to open them on my side. So be patient. Okay, first one. So for the first one, let x1, 2, 3, 4, 5, x5, b, I, d. So identical and then independent random variable. Okay. With exponential of 2. X2. All right, random variable. Like this. Okay. That means they are independent and well, they are exponential type with a rate that is so what it means is independent and f x I at t, it's actually 2 exponential minus 2t for t that is positive. It is 0 if t is negative. Okay. So next, let y1, capital Y1 less than capital Y2, etc. up to Y5. Denote the ordered statistic of those previous random variable. Denote the ordered statistics of xi. So you know what it means. So we want to find the probability that, so the first question is find the probability that, so find the probability that y1 so the y1 is well, less than or equal 1. So the first one. And then next question consists of, again, find the probability find the probability that y5 it's less than or equal 1. Okay. Okay. So there is this formula that the student keep turning around, but I can tell you that if you take other statistic, let me remind you this formula. It's the density f and yk at some y. Look, it is n factorial divided by I think it's n minus 1 factorial. You'll check is it n minus 1 or is k minus 1? It's k minus 1. I didn't memorize it. It's just by because I'm working with this k factorial like this, n minus 1 k factorial. Then with look, that will be f indexed by x1 of y raised to the power, I believe is k minus 1. Then you add to that 1 minus f with again x 1 of y, which is raised to the power, what is the power? Is 1 minus, well, actually n minus k. It's not the y, it's n minus k. It's not over. So the power here, it's n minus k. And then it multiply the density x1 raised at y, like this. So then is it too complicated to have this? I don't think. If you write it down twice, then it naturally will come. So you don't need to memorize anything over here. You can use this formula, okay? Or you can simply use the lemma, which we learned previously. So the lemma on the other statistic for the extreme value y1 and then yn. We learned that. Or you can just use this formula, okay? This formula is not complicated. Once you separate this let's say combinatory number, which is n factorial, n minus k factorial, k minus 1 factorial, then the product naturally comes fx1 at y or at x. It depends on the variable that you have here. So at power k minus 1, and 1 minus the same thing over here to the power n minus k, which multiply fx1 at y. I really didn't memorize anything, okay? So put some effort into that. You write it twice or 3 times on the same paper, you see that become natural to you. But for this case, I'm not going to use it. So I'm just going to use the dilemma from the lecture that we have. So the probability such that the y1 is smaller than a given t. So the lemma said it's if you want the reference for this lemma is section 6.3. So the lemma said that you should have it as 1 minus, well, actually 1 minus fx1, or since they are identical, I'll just call them by f at x at t, which is raised to the power. How many of them do I have? I have 1, 2, 3, 4, 5. Raised to the power n, and in this case, the power of n is 5. That'll be it. Okay. So there is no other point that we should worry about. So then if you want the probability such that y5 is smaller than, I think the second one is it's smaller than 1. Yeah, it's 1 over here. Well, it's not t, but I'll call it by 1. I can put the t over here if you want, but later on we'll specify the value of and the t that equal 1 for the purpose of doing this. So the second probability, so this is smaller than or equal. So this one, thanks to lemma number, I believe it's lemma number 1, yeah. So that will just be, well, it's f x, one of the f, because they're identical at t, raised to the power to the power n, that is 5. Then, so what they want us to be specific about is to find, well, the t equal 1 for this case. Then we're just plugging in the value. If you take p for y1, that is less than or equal 1, your t become 1. So this will give you 1 And then, take a look at what this is. So the one come with, the exponential of 5, which multiply, that will be exponential of minus 10. Okay, so that's P1. And then, as for the second one is a probability such that y is less than or equal, again, 1, like this for the t. And this one is, look, it's said that the rate is 2 exponential. They have exponential of 1 minus exponential of what? Negative 2 over here. You multiply dt equal 1. Then you raise that to the power 5. You don't need to find there is no use of calculator. So you will not do this calculation. Just leave them like that. Any question? Let me see the charts. So someone said, so we should be able to do this differentiation to get the result. What do you mean, my friend? Isn't a factor 2? In the initial equation, where? Oh yeah, there is this factor 2 over there that I just forgot. But mention the 2 over here, okay? Anyway, so someone said we are still expected to memorize all. Look, I never said that. So don't push in that direction. I don't see why you're doing that. There are 1,000 and more of a probability distribution function. So we cannot memorize all of them. Okay. So anyway, yes, I saw your hand. What's up, my friend?
My question is, how did you apply the formula into these two cases?
How?
The previous one, the combination one.
Yes, so no, I mean, you have, so this is a PDF. You know that between the PDF and the CDF, there
Go
is this
down,
rule. Yeah,
go
I'm going
down.
to.
This
No,
formula.
I didn't apply it. I
Okay.
said, what I said was this. This is the formula that, people are saying is too crazy. I say, no, if you want to learn it, just separate it. There is a coefficient factor, okay, which is a combinatory. And then there are 1, 2, 3 factors. So the first one is just the CDF for one of the x, which is x1 in this case. Then you do that one come to the power k minus 1, and 1 minus fx twice, that one come with the power n minus k. And then there is a third term to add. That's it. It's not crazy. So that's all I was saying, okay? But anyway, so let me check something quickly over here, because someone talked about it too. Look, between lowercase fx and the capital Fx. So one of them is obtained as the derivative of the other one. Okay, so if you take the derivative, so if you want to find capital Fx at t, so then you need to take the integral of this expression. So we don't need the 2 over there. Does that make sense, guys? Yes? Because you need to take the integral of the lowercase. You need to take this integral. So these 2 are not there. Move them out. Exponential negative 10. So I'll just checking that. But double check all of the answers. Okay. But that's the general spirit. So then, could you clarify the left-hand side of the equation? P, Y, so the left, you mean this one, right? Could I clarify this one? Yes. So I need to know for the, yeah, okay, yes. No, so this probability is the probability such that the classified, there is so the y1, this is the y1 over here, it's y1 and then y5 over here, okay? So maybe that's what you're saying. It's not just y, it's those index, all right? I think that was the question. So is it top or bottom? So what do you mean by top or bottom? What do you mean by top or bottom, my friend? Because we don't put in the next to the, no, it's at the top. It's a power, right? So the general formula said that, okay, I think I understand. No, the general formula, it's the dilemma. Dilemma said, let me show you. what that is, and then you see what I'm trying to get this from. So that was a 6.3. So 6.3. Okay, let's do that. Yeah, this is the lemma. So the lemma said that if you have p at yn less than or equal y, then it's this formula. And then the next one, the second lemma said if you have this, then it's 1 minus p x1 greater than y raised to the power n. You just need to find that out. All right. And then what I was saying is this, there is a relationship fx at x, which is the derivative with respect to x of capital F. So if you want to take, well, actually f of x, then you come to the integral, okay, the improper integral. Now you should be able to find out. Those are just application of formula. So I think I answered all those questions, unless I forgot some of them. If I forgot, just bring them up, then we can, go over them one more time. All right, so let's continue with the story of these assignment. I hope it is being helpful, because I know, I know that usually around the test like this, the level of the stress is high. So I'm here to help. Don't forget that. Oh, okay. Let me find out the second assignment. Sorry for that. Which one is this? Next, something. Yeah, well, let's do this one. I'll do this one. All right, something simple. Yeah, I'll prefer something that is simple and so you can understand this quickly. First, F, what is the F? Yes, this one. Sorry for, the delay, but be there. Okay. So, all right, let me come back to my old slides. Right. Okay. So let x be a random variable with a probability density function f theta. Okay. So where theta is an unknown parameter, is an unknown parameter with a theta is between 0 and 2. Where the distribution itself, it follow a piecewise function. F theta at x is piecewise. It is in 4x over theta square. Thanks for coming. If the x is between 0 and the theta divided by 2, that is strictly less for this case. It can take the value of, okay. So the second case is negative for x divided by theta square plus 4 over theta. This one is if, look, theta divided by 2 is smaller than x, that is smaller than theta, and 0 for the rest of the case, otherwise. So the first question is to find the MLE estimator by using the moment methodology. Actually find the estimator. Theta tilde, and by using not MLE, but the moment. by using the method of moments. So the method of the moment, I'll answer the question in the chat later. The method of the moment said you need the first moment. Sometimes you only need the first moments to solve the problem. Other time you need the first, second, and third moments. For the most of the case, it's either one single moment or two moments to solve the problems. Okay, usually when there is a single parameter like this, the tendency is to use one single moment, so the first moment. If you have two of them like we did in the gamma distribution, then we use the first and then the second moment. Okay, all right. So, so if we wanted to use the moment, then I need to find the first moment and see how it look like first. So the first moment of this distribution is just the expected value of the random variable. So first moment, it's expected value of x, and that will be, look, is generally the integration over the real number system of f theta x dx. But when you look at the way the function is, then where we only operate within, I think it's 0 and then theta, the rest is 0. So this expected value is the integral from 0 to the first one, theta divided by 2. So the integral from of 4x divided by theta square. So the reason is within that interval, you see that well, the x is going to take the value from 0 to theta divided by 2 plus then theta divided by 2 up to theta, I believe, yes, of f of x, which is minus 4x again, divided by theta square plus 4 divided by theta with what? With dx again, like this. So the rest, you can add the rest of the term, but they are 0, so there is no point. But I'm going to put it. For the rest, well, the one that is coming from r minus this interval, the rest or remaining is just 0 dx, so it cancels this integral over there. Then we'll find that integral. So if we go by antiderivative, the antiderivative of the first term will be, let's see, 4x squared is then 4 divided by 3 x cubed theta squared. The integral is not under, so it goes from 0 to theta divided by 2. Then the first term is a minus and plus, well, plus a minus term, same thing over here, minus 4x cubed divided by 3 theta squared for the first term. Then the second one is where it doesn't depend. Well, I think I get put x here. Okay, otherwise that might not work. This x over here. I forgot. Change that. Okay. So plus plus 2. Let's see. So it's, well, so I have 4x. So that will be 2x raised to the square. 2x squared divided by theta is to be taken between theta over 2 and then 0. So then you operate. So when you do this, the contribution from 0 is 0. That will be 4/3 with actually theta divided by 2 to the cube divided by theta square and then plus. So for the 0 contribution, there is nothing. But so this will be plus 4 4 theta divided by 2 raised to the cube divided by 3 with theta square, same thing as previously, minus minus twice theta divided by 2 square divided by theta. Okay, so that's the first moment. So if you do this calculation, you'll simplify the theta cube and theta square. Okay, with I have here 4 divided by 3, and this will be 1 divided by 2 to the cube. Okay, like this, which multiply. So this, so to multiply theta. We can simplify this into, but later on we'll see. So the same value that we have, is it? So I have 0 here with the minus sign. I come with a positive sign.
So I'm just sitting there like this.
A
Fuck
what?
this guy.
A what?
You're leaving.
I didn't hear you. No? Okay. So it's theta over here, it's not 0, it's theta over here. So if that's one, no, I'll have plus plus first thing first. So how is it? Are there question? So if I'm not seeing this, voice the question, and then I'll know that you have a question to ask. Okay, otherwise I don't know. So if you're plugging in the value of theta here, I'll have, yes, so plug in the theta within this expression. So it will eliminate the cube of theta. Then I'll have a negative, well, actually negative 4 theta. Okay, yes, divided by 3. Plus, if you plus 2 theta, that's the first term, like this. Then I'll subtract that from, if you plug in the theta divided by 2 here, it gives you the same as initially, it's theta divided by 6 with a negative sign, plus theta divided by 2, plus theta divided by 2. Overall, I'll have theta over 6 here, plus minus 4 theta divided by 3, plus 2 theta, like this. So minus theta over 6, plus theta divided by 2. So let's operate on this. So I'll have minus minus here. So this becomes twice the term that I have over there. Okay, so twice is theta over 3. This term with this goes away. And look, I'll have minus 4 theta divided by 3 plus 2 theta, and then minus theta divided by 2. Okay, so if this will simplify to 5. Okay, so I'll have 5 divided by 3 is theta over 3 with, I have this one with this one first. So common denominator is 6, minus 6 over here with 8 theta. So the 8 theta plus 3 theta. Is it plus? Yes, plus 3 theta. Okay, so plus 2 theta, which is somewhere over here. So if that's said, so let's keep operating. I'll have 2 theta minus 8 theta minus 3 theta divided by, this is 6 plus 2 theta. So it is, I have 11 over here. This is minus 9 theta divided by 6 plus 2 theta. So I can simplify. So when you simplify this term, you will get it to minus 3 divided by 2 theta plus 2 theta. So like that. So I hope this is, if you do that, this, okay, you need a minus, this is minus 1.5. So this gives you theta divided by 2. Okay. So the expected value E of X is theta divided by 2. It gives you immediately theta divided by 2. But according to the moment methodology, this should be the sum of the xi divided by n. Okay. So, well, which is x bar? So immediately we know that the theta, we can find the theta because it's a single variable, is 2x bar. So the theta tilde is just 2x bar. 2x bar. Any question, guys? So let's see if the chat contains some question. Okay, I just want to confirm that some of the topic on the practice midterm won't be covered. I can't answer that question. Guys, don't ask those type of questions, right? So I said during the lecture that these are practice problems to prepare for the test. Now, if logically, so whatever is on those tests exceeds topic 6.0 up to 6.4, then just cross those questions out. But if it include anything that we've done in 6.0 to 6.4, then it has the potential. So not that assignment, but the topic is good for training purpose. That's what I said. So again, the study guide is not a predictor of what the test look like. You're just training, doing assignments. The moment methodology here. So I haven't had the opportunity to do this with you. Now it's a good opportunity. Okay. So then let's tackle the second question. Let me go back to and the story over here. The second question asks, is theta tilde from the first part an unbiased estimator? Question is theta tilde an unbiased estimator? Okay, or for theta. Then justify your answer. All right, so if it were, then we learn how to do that. It's E of theta hat that this time depend on the random variable x1, 2, up to n. So it should be equal theta if that is the case. I'm putting an interrogation mark over here to specify that I haven't checked yet. So E of theta tilde x1, 2, up to xn will become E of, well, we said 2 times x bar. So it's 2x1 plus x2 plus x etc. plus xn divided by, I think it's n, like this. Okay, so I can take the 2 to the 2 divided by n out, sum of the e of the sum of the I that goes from 1 to n. By linearity, I can also take this sum out. Okay, so it's 2 divided by n, sum I that goes from 1 to n, e of xi. Okay, so the expected value. But for each of the xi, since they are id, we know that e of xi is theta divided by 2 each time. So that will be 2 over n with sum I that goes from 1 to n, theta divided by 2. So it is 2 over n with n theta divided by 2. So I can simplify all this and I'll get it as theta. So E of theta, a tilde here, of x1 to xn, well, it's just theta. So the conclusion is x or the theta, MLE theta, or tilde, it's unbiased estimator, estimator. It's another story, but it's a cool one. Okay, so let me see if I have stuff in the chat to address. Can you review likelihood? You mean likelihood function? Yeah, I think I did that. So there is another hand that is raised. I'm going to give you the floor. So can I review the likelihood function, right? So the likelihood, when we learn Bayesian theorem, we learn how to calculate posterior uh, and how to guess some prior, especially how to calculate posterior. We learn that. So the likelihood is the likelihood function. That's what you're referring to. We did it, at least I did it for the Poisson case. But since this moment part, I didn't do it for the moment. Okay, for you can do MLE on this. You can do the MLE on this because this is given. So F, you take the product of F of for the theta, then you have to be careful on the boundaries. But this might not be comfortable. The MLE methodology might not be comfortable to find the likelihood, the MLE for this case because of the interval that you have to be careful about. Okay, so the moment strategy is appropriate. If the random variable has one single parameter, then you can stop at the first moment. If it does has several parameters, let's say 2, then you go to a second moment, first and second moment, like we did in class for the gamma distribution. Yes, Jeff?
Can you can you can you scroll down to the
Oh,
the unbiased part?
the unbiased. Okay.
How do you
How do I?
how do you know the expectation of xi is equal to theta
Because he
divided
said
by
that,
square? How do you know
because
it's e
yeah, no, it said that, I found it, right? I found it here. It's a,
okay, I
yeah,
see.
yeah. Very good question. Other question, guys. So someone said, can I review likelihood? Yes, I did. If you watched the video back then we did it for the Poisson distribution. This one over here. So the methodology for, let me just state what the methodology look like for a likelihood function. Okay, the MLE methodology. It consists first of writing the likelihood function L theta. It's the product of I that goes from 1 to n. I to n of fx at the fx theta at xi, like this. Okay, so that's for the general case. And then the next thing that you do is you find the log of capital L of theta. Then what you do next, you find the argmax on theta of log of the likelihood function. And that will give you, this will give you theta hat. To find out that it is unbiased for the unbiased case, then you just need to prove that E, the expected value of, you need to randomize the theta hats. So it becomes a function of x1 to n, like this. Then you get the theta. If you get the theta, then it's unbiased. If you get anything anything more than the theta or anything different from the theta, then it's not unbiased, which means it is a bias. Okay. So can those notes be posted? Of course, I'm going to post both the video and yeah, like request the notes too. Question? Any question, guys? So let's see if I with 6.3. Yeah, the 6.3 notice on Canvas since maybe more than 2 weeks. Okay, it's there. But let me know if you don't see it. And if you don't see it, which I'll be surprised. So then send me an email, I'll send them to you. Lecture 3. Yeah, yes, someone is just helping. Yeah, thank you for the question. All right, guys, I just spent 1 hour here. If I have time tomorrow, Um, if I have time tomorrow, I'll stay over the Zoom in the evening to address some last question. If I don't, then I will not send any email. But in any case, if you come on the, let's say Friday, between 8 a.m. and 10 a.m., I'll be in my office if you have some last minute question, okay? So outside of that, I wanted to say thank you for coming. The exam is not difficult. You're just stressing for nothing. I know that it's not a difficult exam, but you just need to know what methodology. Okay. So there will be, to repeat myself, there will be conceptual question. They are not in the form of, how do you say, how do you call that? So they are not multiple choice question. No, it's just direct question where I'll be asking you to explain a few stuff, but you use a few words. And then there are 4 different problems. The first one, conceptual. Then the 3 other one are on some of the topic that we discussed. Thank you for coming, guys. So I look forward to, uh, if I do have time tomorrow in the evening, I'll let you know. Then I'll be on the Zoom with this same link if you want to ask a question. If I can't, then on Friday, I'll be in my office starting from 8 a.m. Thank you for coming. Yes, Jeff, what's up?
Can you explain what the hold on, I have another question I posted.
Mm.
Can
No,
you
I wanna